Hello, Dr. Elaine. After seeing the stupid mistake I made on assessment 1 and 3 iMovie crashes at the end of my reassessment, I'm starting to think this problem is cursed. But I'm going to try and get through it, just get the video in, and do a better video on a better problem later on. So in class, you asked us to find the electric field due to both of these dipoles, dipole 1 and dipole 2. You gave us a few constants. You told us that let me get on this side. You told us that the charges of the dipoles were 3 nanocoulombs and they were held apart by a rod of length 1.5 millimeters. So I have my information up here. You also put in there that from dipole 1 to X is 10 centimeters across, and well, I guess it's from the middle of dipole 1 to dipole 2 is 10 centimeters across, and the middle of dipole 2 to dipole 1 is 10 centimeters down. So basically, we have everything to start the equation. The only thing I did want to add is um, relative to dipole, relative to X, dipole 2 pulls straight up. So that's where you see this here. Dipole 2 is pulling straight up because the negative charge is closer to X and the positive charge is directly behind the negative charge, so it doesn't really affect the point uh, that much. For dipole 1, you have uh, you have a force pushing down on X from the positive charge, pulling down and towards it from the negative charge. The charges or the pull towards X and away from X cancel out, and you're left with an overall um, downward pull from dipole 2. This is going to be important later when we are looking at the sign, the vector representing these electric fields. So for dipole 1, we're going to use the equation for perpendicular um, electric field. So that's going to be 1 over 4 pi epsilon naught times q times s over r cubed. R cubed is going to be 10 centimeters in this case. Q and S was given to us in the equation, and we know that 1 over 4 pi epsilon naught is a constant, 9 times 10 to the ninth power. Doing all that math, we get 40.5, I believe. Yeah, 40.5 newtons per coulomb. Put into vector form and taking into consideration that you have this downward pull, that gives us 0, negative 40.5, 0 newtons per coulomb. The second step is going to be almost exactly the same. However, we're using the equation for parallel instead of perpendicular, as was the case in the first part of the question. So with parallel, the equation is going to be 1 over 4 pi epsilon naught 2 times q times s over r cubed. So we're basically just adding a 2 into the numerator. Given that R2 is 0.8, that gives us or 0.8 meters, I should say. That gives us an answer of 158.2. Yeah, 158.2 newtons per coulombs. That gives us a vector of 0, positive 158.20 newtons per coulombs. Again, because it's positive because you have an upwards pull. The final step in this problem is to add the vectors together. This really couldn't be any simpler. With this specific case, you're basically just adding 100 and 158.2 to negative 40.5, and that gives a final vector of 0, 117.70 newtons per coulomb.